Let's get started. Welcome everyone. Today we're going to be going over Calculus AB and BC Unit 5 review. My name's Kyle. If you haven't met me already, so also known as jellytheoctopus uh, on Discord. And it's a pleasure to see you all, whether you're joining again from yesterday or if you're new. Alright, let's get started. So hopefully you guys all know about 5 Hive already. Just curious, does anyone not know about this organization? And I'm monitoring the chat for this lecture channel, so that's what I'm going to be looking at. Alright, so basically 5 Hive is an organization that is volunteer student run. So we have many volunteers, and our mission is to provide free resources for students taking AP classes. So yeah, some of us, I hope most of us have heard of it. But yeah, for those who don't know, again, our mission is just to provide resources for AP classes, so practice tests, lectures like this one today. So yeah, you can take a look at these websites and things like that for additional information. All right. So today we're going to be going over Unit 5 of Calculus AB. So that's on analytical applications of differentiation. All right. So before we get into the actual content, so I'm just going to quickly go over how I've structured this lecture. So basically for each of the topics that we have, I have a summary slide prepared, so just some tips and things to remember for this unit and for the topic that we're discussing. And then after, I have 1 or 2 sample problems for each topic, and then we just repeat this for each topic. And feel free to ask questions during any time. Even if I'm talking, I'm going to be monitoring the chat periodically, so feel free to discuss there. And yeah, I'm just also going to send this out now. So we have a lecture form as part of 5 Hive. So this is for the okay, so for your question, if there are other recordings, I know that, so I think the answer is yes if there's already been a lecture on a specific unit. So for example, I did Unit 4 of Calculus AB yesterday, so I have a recording. Speaking of, I have it pulled up. So if you're interested in that, this is the link for you. So that's yeah, Unit 4. And yeah, that's actually a good question, because if I pull up this spreadsheet here, we have all our lectures from 5 Hive. So I'll also go ahead and share this out to y'all as well. I believe you should be able to access it, so please let me know if you can. So for example, we have units 2 and 3 by Cool Savage. So I don't think he linked his lecture recording, but there are some, yeah, so it looks like as of now, I think I'm the only one who's posted my recordings. But to access the practice exams, I'm not too sure where our exams are located, because we are migrating a lot of content to our new website. Yeah, Sec, do you know the answer to that? Has anyone else from 5 Hive? Because I'm not sure where the publicly available content is. I just know, like for us in the organization, we have a Google Drive and everything. So I'll double check. I'll ask my 5 Hive people, my lead, and I'll try to get that information to you. All right. Excuse me. So yeah, coming back to the actual lecture for today. So again, did I send the lecture feedback form? Yeah. So for this lecture feedback form, this is for the end, just to get some feedback from you all. So whenever you leave the meeting, if you have to leave early or if you stayed the entire time, regardless, feel free to fill out that form. It will help me improve as a lecturer, and then also help 5 Hive make these events better. Okay, so let's get into the actual content now. All right, so we have many more topics in Unit 5 than Unit 4. So for those of you who were here yesterday, we have 12 topics to be exact. So we have our mean value theorem, extreme value theorem. Then we go into increasing, decreasing intervals, and extrema. Yes, so Sex sent a website, and yeah, I believe that's the website we're working on. However, we still need to upload some content there. So yeah. Anyways, so where was I? Right. So we have our extrema for this topic, this unit. Then we have concavity in our second derivative test. So um, yeah, all of these are kind of related. Then we move on to graphs of functions and their derivatives. So connecting the function with its first and second derivative, these two kind of go together. Then we have optimization and then also implicit relations. So just since we have a lot of content, I'm curious, does anyone have any specific requests for topics that you'd like me to go over first? Because we don't necessarily have to go in order. Okay, so we've got one request for, all right, yeah, I think we can start off with these two theorems and then we can move to, yeah, related rates is unit 4, so feel free to check out my recording from yesterday where I went over unit 4. And I believe on that lecture spreadsheet you can also find my slides if you need. Okay, so let's start today off with the two theorems and then we'll move down to optimization. Then I got a request for 5.7. So yeah, so let's start off with those topics. Okay, so mean value theorem. All right, so first of all, what are our conditions of the mean value theorem? We have two main conditions. So the first is we have to make sure our function is continuous on the closed interval a to b. So notice this is a closed interval, so we must include our endpoints. The second condition is it must be differentiable on the open interval a to b. So notice this is an open interval, so the endpoints are not included. So if we have these two conditions satisfied, then what the mean value theorem proves is we have at least one point C on the interval a to b such that f prime of c equals fb minus fa over b minus a. Okay, so just looking at the equation, it might be a bit confusing, but if we think of it in different contexts, that will help us to understand a bit better. So if we just think of it in terms of what is f prime of c, so f prime of c is our derivative, and remember derivatives are instantaneous rates of change. So our instantaneous rate of change is equal to this expression, and recall this expression is our average value expression. So it's the average of the function f from b to a. So what the mean value theorem is saying, put simply, is there must be some point where the instantaneous rate of change is equal to the average rate of change. And we can also think about it in terms of geometry or graphically. So if we think about it in that case, our derivative is our tangent line. So the line that's tangent to a single point, it must be parallel to the secant line connecting points A and points B. So that's our basically our average value. So you can also see in this diagram here, our secant line from A to B is this orange line, while we have a tangent line here at point C, and notice that these two are parallel. So in other words, these two slopes are the same. So that's why we have that they're equal in our statement here. So hopefully these different representations are making sense. And by the way, note that it is at least one, not necessarily only one. So for example, in this graph here, if you look at this top of the pink curve, it's possible that we have another tangent line that might be parallel. So just remember that we may have more than one point. Okay, so far, are there any questions? Again, feel free to put questions in the chat anytime. Okay, so moving on, we have Rolle's theorem. So this is just a very special, a very niche case of the mean value theorem. It's basically where we have f of a equal to f of b. So honestly, you don't really have to memorize this on its own. It's just a special application of the mean value theorem. So in case you still need some uh, visuals, so basically if we have a graph, so let me draw a random curve, and if our 2 points of A and B, if they are equal, so if f of A is equal to f of B, you can see our line is completely horizontal. And then using Rolle's theorem, we might be able to say, okay, here's one value of C, here's another value of C, etc. So again, don't worry too much about the actual terms. Just know it's the same thing as mean value theorem, just with an extra condition. And then finally, I just have some potential applications of this theorem. So one is proving the existence of certain points. So it might, so on your test, you might see a question where it gives you A and B, and then it says, oh, can you prove that there's a point where you have a certain slope? So in that case, it's likely going to be mean value theorem. And another application is proving properties. So most of the time that's with our real world applications, and even more of the time it would be our particle motion. So things like if we have our velocity and we have to find matching our velocity equaling an average speed. Okay. So the mean value theorem for integration, I'm not sure if it's covered in this unit. So honestly, when I learned mean value theorem uh, through my own calculus course, my teacher said that honestly you won't really see mean value theorem for integrals. So mean value theorem for integrals is pretty much our average value formula for integrals. So just going over that, if we have a function and we want to find the average on, let's say, the interval a to b, that's just our average average function equation or formula. Yeah, exactly. As Sage mentioned, it's our 1 over b minus a times our integral. So this is just a quick review of average value. So honestly, I'm not even sure if you'll ever need mean value theorem for integrals, because I think most of the time you should be able to just use this average value formula. So yeah, hopefully, sorry, that wasn't a very conclusive answer to your question, but hopefully just reviewing this will help, because in 99% of cases, yeah, because from my own experience, I've never actually had a question where I've had to do mean value theorem with integrals. I've always just done the average value formula. So anyways, hopefully that's a nice review on the integral side of things. Okay, so now that we've covered the mean value theorem, yeah, so I think my experience is similar to other people. Yeah, so coming back to this sample problem, let's try to work this out. So feel free to try and solve this problem on your own at first, and then I will go over the solution in a little bit. But first, I'll give you some time to work it out on your own. Okay, so in this problem, we have a function f of x on this interval from 1 to 3. So first, we want to verify that we can use the mean value theorem. And then once we verify that, we want to find all values of c that satisfy the condition of the mean value theorem. And for those of you who are new today and haven't joined my lecture yesterday, for these sample problems, if you need help, I just added some guiding questions, some hints if you need them. So in this problem, if you're a bit stuck, first focus on what the derivative is, and then remember for our mean value theorem, our two conditions are continuity and differentiability. And then also try to recall whether it's an open interval or a closed interval. So just some guiding questions for you. And when you have a solution, feel free to let me know in the chat. And if you want, you can put it in spoilers. So I believe that's with the absolute value sign. No, what is it? Oh yeah, so if we have the two bars, you can put it in, what's the word, spoilers. But anyways, it's optional. Okay, so we got one answer. So I believe, Jello, you mean that our C value is 2, right? And then you made sure to prove that the mean value theorem applies. Okay, no worries, Sage. We all forget things. So that's why it's always good to... Oh, okay. Wait. Okay, yeah, anyways. Sorry, I got distracted by something. Oh wait, so do you need me to remind you of the formula again? It's here. Oops, let me. So I'm just gonna quickly go back to the. Oops, and I think I leaked the answer. So this is our formula again. So try to remember this if you can, or just note it down somewhere, and then review it. So it's our b minus a. Yes, sorry, were you asking for the mean value theorem or for, I mean for the not differentiable, for derivatives. Sorry, I'm getting lost in my thoughts. Yeah, by the way, so just one quick thing. If you also forget this formula, if you use the fundamental theorem of calculus, we have the antiderivative of b minus derivative of a over b minus a. And then this is the same thing as our average formula for slopes and things like that. So just an extension. Okay. All right, sorry. I'm kind of going on a lot of different tangents. Yeah, this is our formula for the mean value theorem. So hopefully this helps. Okay. And yeah, sorry, I keep on leaking the answer to you guys. So have we all managed to solve this problem, or do we need more time? I think some people sent their answers. Okay, well, I hope we all at least were able to attempt the problem. So congratulations for those of you who got 2 as your answer. 2 is indeed correct. More specifically, I should say there's a point C equals 2 where the slope is equal to the secant line. Anyways, alright, so to solve this problem, we first should prove that mean value theorem applies. So f of x is a polynomial, and that means it's continuous on its entire domain, and thus it must also be what did I do? Okay, it must be continuous on the closed interval 1 to 3. So hopefully that makes sense. Since if it's already continuous from negative infinity to infinity, this is a subset or a subsection of that larger domain, so it should also be continuous here. And then f prime of x, our derivative, is also a polynomial, so it's continuous on 1 to 3 as well. And so if you recall our definition of differentiability, if our derivative is continuous, then our original function is differentiable. And so now we've proved continuity and differentiability, so we can use the mean value theorem. And then plugging into our formula, we should get, so simplifying this right side, that's our average formula, we should get 6. And then if we plug in 6 to find a point C through our derivative, we should get 2. So hopefully this solution makes sense. Again, please ask questions if you have any. Okay, if not, let's move on. Okay, so are all non-continuous functions non-differentiable? I think Yes, just because I can't think of any case where that's not true. Oh yeah, for sure. So here's the original question. So okay, so to answer the question of non-continuous functions, well, so in the case of mean value theorem, if it's not continuous, you don't need to go back, um, or rather, you don't have to prove that it's not differentiable, because if one of our conditions isn't satisfied, there's really no point in proving the others. So I'm not sure in general if there is a special case. My gut feeling is no. Um, so I believe if it's not continuous on the same interval, if you take the derivative, it shouldn't be differentiable. But again, don't quote me on that. There might be a special. Um, yeah, I think so. Actually, that's true, right? Because our definition of differentiability means it must be continuous. Yeah, thank you, Sage, for reminding me. That's true. Yeah, so if you review differentiability and continuity at a point, I believe you first need to prove continuity and then you can prove differentiability. Okay, so let's get back on track with the extreme value theorem. So first of all, what are our conditions for extreme value theorem? So we just have one condition this time. If it's continuous on the closed interval a to b, then what does the extreme value theorem guarantee? Then it guarantees there must be an absolute maximum and absolute minimum on a to b. And so these maximum and minimums could occur at our endpoints or critical points. And I believe on the next slide I'll elaborate a bit more on what these terms mean. Uh, right, so first getting the definitions between global and local extrema. That shouldn't say extreme. Let me fix that. So our global, also known as absolute extrema, so those two terms are synonymous, and can be used interchangeably. So global slash absolute extrema, those are the highest or lowest points on an entire domain or the entire interval. So depending on what the question is asking. Yeah, there's it's not too bad. I think there's only two tests for max and mins. Um, right. So the opposite would be our local, also known as relative extrema. So these are max and mins, but they are just higher or lower than nearby points. So to give a visual representation of the two, let's say we have a function like this. So let's say this is our function. So for this point here, would this be a relative extrema or a absolute extrema? What do you guys think? All right, so we got some answers. Yeah, so I hope we can all see that it's relative. So although it's a maximum, it's not our absolute maximum. So you can see where the terms are coming from. Because our absolute maximum on this interval would be up here. So just always make sure to keep the distinction between relative and absolute extrema very clearly. And yeah, so endpoints in this theorem, extreme value theorem, are they are indeed included. So yes, endpoints or critical points. Here I was just trying to highlight the distinction between critical points and, sorry, not critical points, between local extrema and absolute extrema. And yes, to answer your question, there can be multiple relative extrema. So for example, in this case, we can see there's two relative extrema here because this is an absolute max. Sorry, this is a relative max, not an absolute max, because we can see it's greater than all the neighboring points. This too is also a relative extrema because it is greater than the points around it. And in addition, this point would also be a relative extrema because it's a relative min because it's smaller than all the points around it. And one thing I want you all to remember is that our absolute extrema can be relative. Actually, our absolute extrema are always relative extrema. However, relative extrema may not be absolute extrema. Does that make sense? It's kind of where a square is a rectangle, but a rectangle isn't necessarily a square, because absolute extrema are a relative extrema. However, there's one more condition, that it must be the greatest one out of all the relative extrema, either the greatest one or the smallest one, depending if we're talking about max or min on the entire interval. And to answer the question if endpoints are considered relative extrema, so endpoints typically we don't consider them as relative extrema, because relative extrema, the condition is it must be greater than all the points around it or less than all the points around it. So I think most of the time we would just avoid trying to classify an endpoint as an extrema or not, just because one might argue we don't know what's on this side of the graph. Because if I give you a graph, let's say, okay, so let's say I have a graph here, and let's say this is just a specific interval. I don't give you the entire graph. So you might say, okay, is this a relative max or min? But that's all dependent on whatever's on this side of the graph. Because what if it goes like this? Or what if it goes like this? What if it goes like that? So my answer would be no, because we try not to classify endpoints as relative extrema. However, for endpoints, we can classify them as absolute max and absolute min, because in that case, we just care about the interval itself. But with relative extrema, since we can't compare with the other side, the side that we don't know, it's very hard to determine. So does that make sense? Okay. Great to hear. All right. So again, if you have any questions, please continue to ask. But if not, let's move on. So yeah, so now to the actual definition of our critical points. So critical points are points on our domain or interval, so depending on what is asked. So if it asks on the entire domain, we would focus on the entire domain. If it asks, oh, just on a specific interval, then just focus on that specific interval. So it's either where our derivative is 0 or our derivative is undefined. So most of the time people remember the equals 0 part, but sometimes I would say more often than not people forget that it can also be undefined. So please try to remember that critical points, we have two possible definitions. Sorry, let me close something. Okay. And so why do we care about critical points? Because critical points are our candidates for local extrema. So local / relative extrema. And one important thing to remember is that not all critical points are actually relative extrema. So don't rush during your exam and go, okay, I found my critical points and those are all my relative extrema, because that's not necessarily true. So we always need to test them using one of our tests to ensure that they actually are a relative extrema. So we'll go more in depth on these tests later on in today's lecture. So just to give you one quick case of where a critical point isn't necessarily a relative max or min, so a relative extrema. So let's say I have so I believe this is an x squared graph, but correct me if I'm wrong. But regardless, let's take this graph. So here we can see that since it's completely flat, our derivative here is 0. However, even though our derivative here is 0, so it is a critical point, yes, but is it a relative extrema? No, because it's neither a max or nor a min. So this is just one case to show that our critical points aren't always our relative extrema. So hopefully we get that part. Well, so points of inflection. So yeah, in the case that I just drew, that would be a point of inflection because we're changing concavity. However, I, I can't remember the exact definition of points of inflection, but I don't think they're that related to critical points. So that's also one topic where you want to kind of keep the definitions clear, because points of inflection are more related to the second derivative, while our critical points are more related to the first derivative. Um, so yeah, I'm trying to remember if the definition of a point of inflection has a critical point. I don't think so. I think for points of inflection, the criteria is as long as the point exists and we change concavity, then we have a point of inflection. So that's that definition, and that's a little bit different from critical points. So hopefully that just clears up any confusion if there was any. But yeah, okay. So if we don't have any questions, let's move on to this sample problem. So here I have a function f of x. So first, prove and make sure that we satisfy all conditions of the extreme value theorem. And then once you prove that, find all the critical points of f of x. And I'm always paranoid that my recording gets stopped. Sorry, that was just a digression. Anyways, yeah, we're still recording, so we're good. And yes, so if you need some guiding questions here, first, what is the derivative of f of x? And is our function continuous? And also, what is the definition of a critical point? So these are some things to help you. Yeah, in this case, there's no interval, so just take the entire domain. Yeah, so make sure you check if there's any discontinuities on the entire domain. And yeah, so that's a good thing to remember. If they don't give you an interval, you can assume 99% of the time it's going to be, or I'll even say 100% of the time, because I'm not sure how else they expect you to interpret the problem, besides just using the entire domain. Okay, so again, whenever you get a solution, please share in the chat. And yeah, you can use spoilers or not. To be honest, it doesn't really matter because we're going to go over the answer anyways. The more important part is making sure we remember our conditions for how to prove the different theorems, because that would be worth more points on things like FRQs. Okay, so we are struggling with part A. All right, no worries. So let me just see if anyone else has a solution. If not, we can take a look at the solution together. Sorry, I just took a sip of water. Okay. So any more answers? Actually, you know what? I think that's true on what Viper is saying. Actually, let me think. Is that? I think, yeah, that might have been my bad. Okay. I think, yeah, so you can still find the critical points. However, the extreme value theorem, that part you would actually need an interval. Sorry, that was a very good catch. Because I believe for mean value theorem, oh no, not even for mean value theorem. Sorry, have I been saying the wrong thing on... Oh, okay, no. So, yeah, what I did wrong was for the critical points, you don't have to worry about any interval, but for the actual extreme value theorem, we would need an interval. So, let's just say from -4 to 8, let's see. So, hopefully, so yeah, thank you. It was Viper who noticed that. So yeah, here I'll just say all the critical points of f of x on its entire domain. Right, so yeah, even I got confused there. So again, what I got wrong was for critical points, you don't need an interval. However, for extreme value theorem, you do need a closed interval. So sorry if that confused anyone. So let me see, what did I even put for my... Oh wait, so I did have an interval here. Did I just delete it? Okay. Sorry, that's weird. I think I might have just forgot to add that earlier. So yeah, let's say on 0 to 3. Right, so our solution, since f of x is a polynomial, it's continuous on its entire domain, so it must also be continuous on 0 to 3. So extreme value theorem applies. And once we take our derivative, and we get this, so 3x times x minus 2. If we set this equal to 0, we have x equals 0 and x equals 2 at critical points. And in this case, since f prime of x is also a polynomial, we don't have any discontinuities, so it's not possible for there to be any cases where it's undefined. Okay, sorry, I haven't really been checking the chat. So hopefully I'm not missing any questions. Okay, so hopefully this makes sense. If not, please let me know, but if so, let's move on. So that was the first two topics. So I believe after these two, the next request was for optimization. Is that right? Okay, so I think the questions in the chat. So a polynomial is always continuous, so there's no there's no discontinuities. However, so a rational function, so is that like 1 over x, or... But yeah, basically if you have a fraction and there's something over x, let's say, then there may be a discontinuity. Yeah, so I think in the previous units they go over continuity, discontinuity, differentiability more in depth. Okay, right. Yeah, so if we have a polynomial over another polynomial, we may have discontinuities. Okay. So hopefully we understood those two theorems. Let's move on to optimization. And it's already been 30 minutes, so I'm not sure how many topics we can get through today. Let's just try to go as fast as we can. But again, let's not rush either. So, okay, so Rolle's theorem is just the mean value theorem where f of a equals f of b. So for cars, if you have any more questions about Rolle's theorem, feel free to ask if you have any specific questions. But simply stated, it's just the mean value theorem with where our two f of a and f of b are the same. So hopefully that helps. Okay, anyways, let's focus on optimization now. So the idea of optimization is finding the maximum or minimum value of a functions given some certain conditions. So some contexts you might see in business or finance, maybe something about minimizing cost. Engineering, maybe we have to maximize the area of some material. And there's many other applications where we might see this. Okay. So hopefully that makes sense. That's just a quick overview of what optimization is. So now moving on to actually solving optimization problems, here are some steps and some tips um, on how to solve these problems. So first of all, we need to understand the context and understand what the problem itself is. So what are we trying to maximize or minimize? What variable or what quantity? And if possible, try to draw a diagram. And then that way it will help you visualize relationships between variables. And going along with drawing a diagram, we should, of course, define variables for different quantities in our problem. Then after these steps, what we want to do is to create an objective function. So this is the function that we're trying to optimize. In other words, this is the function we're trying to maximize or minimize. And we'll go over a practice problem. So if these terms are still seeming a bit confusing or you can't really remember what the process is, we'll go over a problem and hopefully that helps. Okay, after we have our objective function, we have some constraints. So these are equations relating different variables in our context, in our problem. And then this way we can eliminate variables in our objective function until we have a single variable, and that will allow us to differentiate. So take the derivative. So that is our next step. Then finally, we want to use the first or second derivative tests. Okay, well, we haven't gone over the first and second derivative tests yet. So do you all want to first review those two, or do you guys think it's okay if we first finish the optimization? It's up to you all. Okay, so okay. Okay, so far I'm hearing just finish. Okay. I think some are saying to finish the test. So I think so far the majority is saying finishing optimization. So I'm just gonna go with the majority. Sorry for those of you who need um, a review on the first and second derivative test. Well, regardless, when we solve these problems, I'll also go over the test a little bit as well, and then we can go back and review further in depth. So I hope that's okay with everyone. And yeah, last step, we just want to answer our question with units. Okay. Hopefully these steps are, if they don't make sense yet, hopefully they kind of bring back some memories. And if we are feeling ready, let's try to solve this sample problem. And so actually, since I'm not sure how well you guys are in optimization yet, would you like me to first, or actually let me see, how many sample problems do I have? Okay, well I only have one sample problem. So do you guys want to try this on your own, or do you want me to just go through the solution off the bat? Okay, so I think we got one. Okay, we got a few people wanting to work on it on their own. So feel free to do your best. And I'm not sure, maybe I should go over the two tests. Here, let me, okay. Oh, okay, well, so even if it's the same question, hopefully, well, yeah, so then you know the ideas to solve this problem. Hopefully it won't be too bad. Yeah, I just want to quickly go back and double check which topics we have. Okay. Yeah, so after optimization, we can go through these topics on first derivative, second derivative, and the different tests. Okay. Let me come back to this problem. Excuse me. Yeah, Minecraft, because it's blocks. But technically this is a rectangle, right? So, is it the same exact question? I'm curious because I just chose random values for this. Okay, that's weird. Uh, really? Okay. Well, yeah, I hope no one's. Well, I mean, I already passed AB, so um, don't worry, I'm not cheating or anything. But hopefully you guys aren't cheating either. Anyways, I think it's just a coincidence. Yeah, this is a very common type of problem, so um, who knows? Maybe I'm just lucky. But yeah, so please let me know once you have a answer so I can just kind of get a sense of where everyone's at. Yeah, I'm curious, does your calculus teacher make the tests on their own, or yeah, I guess I think 120 is a nice number. When I solved for it, it was very easy. Okay. I don't know. I think it's just a lucky coincidence. Oh yeah, so by the way, hopefully you all are still working on this problem. So again, just the steps we can take. So first, what quantity is being optimized, and then what other variables do we have? So making sure we define all the variables in this problem. And then creating our objective function, that's the next step. And also finding any other constraints or equations. Oh yeah, hopefully we're not doing any integration today because we haven't gotten to integrals yet. I think that's units nine, not nine, units 6 and beyond. Right, so once we have our objective function, our constraints, then we can prove maximum and our minimum depending on whatever uh, context we have. So in this case, we want to maximize. And yeah, then at the end, just answer with units. Are you guys on unit 9? Yeah, I'm taking BC this year too, so we'll see how the test goes. Yeah, I'm a junior, if that was for me. No, I'm taking, well, I didn't take AP Chinese. I'm taking AP Chinese this year, but I did take a Chinese class in freshman. Uh, yeah, so by the way, has anyone finished this problem? Just because I haven't seen any answers in the chat yet. Um, oh, if you guys need to self-study Unit 9, maybe I can do a lecture session on Unit 9. I'll see if someone else is doing Unit 9 already, but so yeah, so has anyone finished this problem? I just don't want to be wasting time if everyone's already finished. Or even if you don't want to share your answer. Um, or yeah, if someone could just confirm if you finished the problem or not, I don't want to be taking up too much time. Okay, so one person has finished. Okay, yeah, sorry, because I felt like I was just waiting a bit too long. Okay, so we've got the final answer of 1800 meters squared. So for this problem, how I solved it, I had two variables, x and y, for the width and the length. So you can see here in this diagram, I have my x and y. So my x is my width, so I just labeled it as w here, but it's the same as x. And then my y are my lengths. So the important thing to notice here, yeah, I'm a great artist, I know. I'm taking commissions. I don't know why the cow is outside. I couldn't fit it in. Anyways, so yeah, so the important thing to notice here is that we only have one length because one side we don't have to put up any fences because that's near the river. Okay, so our constraint was how much fence we actually had. Oh, okay. Um, I don't know. I think today's just a coincidental day. Anyways, so our constraint is we have the two widths plus the length has to equal our total amount of fence, and then our objective function, this is what we're trying to maximize, is our area. So we know that area is equal to the width times length, and if we use our constraint equation, we can substitute such that we just have a single variable in terms of x. We have our area in terms of x. So where's the square? Um, so here we have, yeah, that's a great question. So since we know that our 2 times the width plus our length is equal to 120. So if we find what is y in terms of x, we know y is equal to 120 minus 2x. And then if we plug into our area function, so we have area of x. Area in terms of x is equal to our width times, and then length, we can plug this in. And then once we multiply this out, you can see where we get the x squared. Did I make a mistake here, or? Sorry, wait, just to confirm, did I make a mistake here, or are you guys talking about your own solutions? Okay, what was the mistake? Okay, I see what I did. Right, yes, so there should be an x. Thank you, good catch. So let me see, did I do everything else correctly? Um, okay. Oh yeah, a prime of, sorry. Right, so a prime of x should be 120. Okay, and then, right, so then after we take our derivative, we can find the critical point, so setting it equal to 0. So we have x equals 30. And then here I did the second derivative test. So if we take the second derivative, a prime of x is equal to -4. So no matter what value of x I plug in, it's always going to be -4. Since this is less than 0, we have a relative max. I think, wait, no, this should be concave down, right? Or am I? Because it's negative. Yeah, it should be concave. Sorry, yeah. So since our second derivative, okay, how I found a of x. So since we know our objective function is our area, x times y, or width times length, and our constraint equation is 2x plus y equals 120, because our two widths plus the length has to equal 120 meters. And if we find y in terms of x, so y equals 120 minus 2x, we can plug that in for y and multiply it out to get 120x minus 2x squared. Does that make sense, or do you need me to write it out? So the last part is just, so for example here, if we have y in terms of 120 minus 2x, if we plug this back into x times y, then we can just multiply these two and get 120x minus 2x squared. Okay, hopefully it makes sense now. And yeah, okay, so coming back to second derivative test, since I proved this is concave down, so we have a relative max. And then one thing we'll go over is that if we have a relative extrema and it's the only relative extrema, then it's also the absolute extrema. Well, so to explain this concept, let's say I have a function with a single relative extrema. So let's say here I have a relative max. So since you can see this is our only relative extrema, there's never going to be a chance that it comes back up and that there's another maximum, because if that was the case, then there must be another relative extrema at least. So if we can show that we only have a single relative extrema, we can just say then this must be the absolute extrema as well. And yeah. So then once we prove that, we can show that, or rather we've proved that this is our best width, so we can substitute that into our constraint equation to find what is our length, and then these two are our optimized values. And yeah, quadratics always have one relative extrema, yes. And then yeah, so just multiply these two and that gets our area. So does this make sense to you all? Is optimization coming back or making more sense? I hope so. And actually, so I just realized one thing I didn't touch on yet was the domain. So sometimes instead of using the first derivative test or second derivative test, you may need to use limit instead, depending on your domain. If you have a open interval, then you would need to use use a limit. Oh, okay, go back to the problem. Yeah, for sure. So do you guys understand that part of just making sure you know what the domain is? So in our case, so the theoretical foundation behind optimization. So basically with optimization, yeah, I can quickly review once more. So again, it's just trying to find a maximum or minimum value of some function given some conditions. Yeah, so Sage, the domain would be 0 to 120 because you can have 0 width, let's say, and 0 length, but you can't have negative. And yeah, so since we have closed brackets, we can use our we don't need to well, so if we use the first derivative test, I think we wouldn't need limits, but since we're using the second derivative test, it doesn't really matter. Yeah, so that's kind of where EVT comes in as well. No, it doesn't have to be. However, in that case, you would just have to use limits instead of plugging in. So yeah, that's kind of similar to EVT. Yeah, so there's a lot of different concepts at play. So I'm not too sure how to explain them all at once. Okay, here, let me just get one thing at a time. So for those who just joined, so again, optimization, when we solve optimization problems, we just want to define all our variables, and then we have an objective function. So this is a function we're trying to maximize or minimize. And if we also need to make sure and check if we have any constraints. So this is just equations relating other variables. And then we can substitute these and eliminate variables in our objective function until we have a single function. And then we can take the derivative and then use one of our tests to find a max or a min, and then answer with units at the end. So for those who just joined, hopefully that makes sense. Or is there something else that I didn't go over? And yeah, so let me try to explain the domain part. So I think one of the faults of me solving it this way with the second derivative test is since this was our only relative extrema, we didn't need to prove the endpoints. However, if we want to use extreme value theorem, we need to prove we have closed intervals. So if we have a domain that's on a closed interval, feel free to use EVT. However, in some cases, we might have open intervals. So maybe we have 0, or maybe we have infinity. Or it doesn't have to be 0, but if we have open intervals, in this case, we can't use EVT here. because we don't have a closed interval. So what we have to do is we still find the critical points, but instead of checking the endpoints, instead of just plugging in, we have to take limits of any side that's an open interval. So hopefully your teachers went over this part. Hopefully this is just a refresher. Does this idea make sense to you? And yeah, the function should have a max or a min. I doubt they will ever give a problem where there ends up not being a maximum or minimum. Oh, really? Wait, so in AP. Okay, anyways. So, yeah, just getting back on track, does this make sense to everyone with checking the domain and when we can use EVT, when not to use EVT, and if we can't use EVT, what to do instead? So yeah, just be mindful of what the domain is in the context. So if we have an open interval, remember, don't use EVT. So you could either use what I did with the second derivative test, or you can use limits. So there are many different ways of solving optimization, as you can see. So again, to recap, we have our first derivative test. Well, first derivative test and EVT actually go hand in hand, so those are kind of similar. And yeah, and then the other one would be second derivative test, and if we have a single extrema, we can say that's the absolute extrema, so that's what I did here. And then one more option is we find critical points and also take the limits at our so-called endpoints, even though if it's not a closed interval, they're not really points, but we can take limits. So yeah, that's kind of a recap of the different strategies of solving optimization. Okay. And by the way, if anyone, I think some people have left, but there was that form. Yeah, I'll just send it again. Just another reminder, if you could fill this out whenever you leave, that would help me out a lot. Okay, so hopefully, are there any more questions about optimization? Okay, so you don't understand the second derivative part. I think, so we're gonna go back and cover um, first derivative test and second derivative test. So I'll elaborate more on that if that's okay. Okay. So what we have yet to cover is 5.3 to 5.9. So I think unless if there are any other requests, let's try to just go through these at a quick pace, and hopefully we can cover them all in not too long of a time frame. So let me check. Okay. So here's my 5.3. All right. So we're kind of taking a step back from optimization and all of those more involved topics. So let's just review the basics. So starting from increasing and decreasing intervals. So to find our intervals of increasing and decreasing, we first want to take the first derivative, and the reason is because we need to find our critical points, because that's when our derivative is neither, or rather, that's where our function is neither increasing nor decreasing at our critical points. And then we can use a sign test between the critical points to find where f prime of x is greater than 0 or less than 0. So that means if it's increasing or decreasing. So hopefully this part is reviewed as well. And then again, depending on what context or what problem you're solving, just make sure you're keeping in mind what the interval is or what the domain of the function is. Okay, hopefully this makes sense for you all. And yeah, so if so, let's solve this problem. Hopefully this isn't too difficult. So we have a function f of x, so try to find all the intervals where the function is increasing and decreasing. Alright, so actually, do you guys want to solve this problem, or should we just move on to something else? Okay, so if the function is more than a third degree, I don't know, you might have to use some pre-calc skills or things like that to factor your, or I'm not sure if that's in pre-calc. I'm not sure when they teach factoring, but there's some different factoring skills you can try to use. Yeah, I think, uh, yeah, it might be Algebra 2. I'm in California and we have the integrated math system, so it's a little bit different. Um, yeah, there might be a graphing calculator question. Well, in that case, it kind of defeats the purpose of this type of question. Yeah, so most of the time they won't ask where it's increasing or decreasing. This is just a prerequisite for different um, different tests. So more specifically, this is one condition for the first derivative test. Okay, so have we solved this function, solved this problem yet? Okay. So yeah, maybe another 30 seconds. And yeah, I don't remember the exact solution, so we'll take a look together. Okay, yeah, I think Viper agrees this 1 to 3 is decreasing. Okay, I think at least some of us have solved the problem. Okay, so here's the solution. I believe, yeah, I think all of you are correct. So congratulations, it's increasing on negative infinity to 1, then 3 to infinity, and decreasing on 1 to 3. So the way we can solve is first take the derivative and then find our critical points. Then just test values in between our critical points. So for example, 0, 2, and 4. And we can test whether or not these intervals are increasing or decreasing. All right, so hopefully this makes sense. If so, let's move on to the first derivative test. So the reason we went over finding increasing and decreasing intervals is for this test. So the first derivative test is to find relative/local extrema. So the first step is to find our critical points, and then we use the skills from the previous topic to find where's our where's our function increasing on what intervals and what intervals is our function decreasing. So what the first derivative test tells us is if at a certain point, if the derivative changes from positive to negative, so from increasing to decreasing, then we have a local max. On the other hand, if we have one that changes from negative to positive, which means decreasing to increasing, then we have a local minimum. And then if there's no sign change, then we don't have a local extrema. So hopefully this makes sense. And yeah, that's a lot of APs. Good luck to you. 1, 2, 3, 4, 5, 6. Wow, 6 is a lot. So good luck for you next year. Okay, anyways, let's try to solve this problem. So using the first derivative test, can you find all the local extrema? So let's all try to solve this problem and let me know once you've finished. And yeah. So I don't want the session to go over 2 hours. So let's just, yeah, we'll see how many topics we can get through. So yeah, again, please make sure you're working on this problem and then let me know once you've got a answer. Did we already do this problem? Oh, okay, yeah. I think the function should be different from the previous ones. I think it's a little bit different, unless if I'm misremembering. By the way, these questions here you don't have to answer. These are just guiding questions. The main question is to find all the local extrema. So we want to find where do we have our relative max, where we have our relative mins, and so on and so forth. Excuse me. And hopefully Do you guys still need a minute or a few seconds, or should I show the answer? So again, it's good that you guys are finding the intervals, but just remember that the final answer should be where do we have our relative max and mins. But yeah, it's good that you guys are finding increasing and decreasing. So let's just go over the answer. So our local max are at x equals 0 and local mins are at x equals 2, because we can check our intervals, and we can see at x equals 0 it changes from positive to negative. So that's our local max because it goes from increasing to decreasing. On the other hand, at x equals 2, it goes from negative to positive. And since that's decreasing to increasing, we have a local minimum. So hopefully this makes sense. Okay, so our next topic is candidates test for global extrema. So again, global extrema and absolute extrema are the same thing. So we're trying to find our absolute slash global extrema with this test. So the condition is we must have a closed interval on A to B. And the steps for using the candidates test: first, we want to take the derivative, find the critical points, so similar to everything else. Then we evaluate the function of f of x at the critical points and endpoints, and then we compare the values. So whether it's the greatest value for the maximum or the lowest value for the minimum. And so this, if you were here for the optimization part, we pretty much have already been doing this test. This is just in a more general context instead of optimization. But if you recall, optimization, we used, well, how I solved it, I didn't use this test, but in optimization you may have used this global extrema, what's this called, candidates test for global extrema. Okay, and then one more thing. So EVT and candidates tests are actually very similar, because if you first use EVT, that will actually help you with your candidates test, because EVT, it proves that we actually have a max and a min. Then the candidates test is actually finding those absolute extrema. So most of the time how I would solve these types of problems, I would first use EVT to prove that a max and minimum exists, and then I would just plug in the critical points and endpoints. So in other words, typically you should cite the extreme value theorem. However, for candidates test, since it's a test and not a theorem, you can just do it without actually having to cite it, if that makes sense. And let's try to solve this problem now. So we have a function, and find the absolute max and minimum of f of x on the interval 0 to 4. So let's see. Um, yeah, so reading sent a more comprehensive um, definition. Um, okay. Anyway, so has anyone managed to solve this problem yet? Or are we still working on it? Um, and again, hopefully you are taking the derivative, finding the critical points and the endpoints, and plugging them in for candidates test. Yeah, I'm not seeing any answers in the chat, so just making sure you guys are still working on it. If not, we can look at the solution. Okay. Alright, so we got one answer. Anyone else? If not, we'll take a look at the solution. Okay, I think we agree with Sage here. Alright, let's take a look at the answer. So absolute max at f of 4, and the value is 17. Then our absolute minimum, f of 2, is negative 3. Did I make a mistake here, or... It's possible I might have made a mistake. Here, let's look through it together. So our derivative should be 3x squared minus 6x, right? Yes, and if we factor, we have 3x times x minus 2. Okay. So our critical points are 0 and 2, and our endpoints are 0 and 4. Also, this is an important thing to remember. Sometimes our critical points will not be on our interval. So if we had, let's say, 0, 2, and 8, we shouldn't test 8 because 8 is outside of our interval. So just always make sure that our critical points are between our two endpoints. So in other words, that it's on the interval. Okay, so if we test all our points, we have f of 0 equals 1, f of 2 equals negative 3, f of, sorry, so I think that's negative 3, and f of 4 is 17. Okay, so hopefully everyone understands this part. And yeah, sometimes arithmetic is the hardest part of calculus, so no worries there. Okay, so now for concavity. So concavity is relating our second derivative. So just going over some definitions. Concave up, the graph is opening upwards, so like a cup, concave up, if you need that, if that will help you remember. And then concave up is when our second derivative is positive. Then concave down, which means the graph opens downwards, so like a frown. And yeah, typically this is how I remember concave down. It looks like a sad face. Yeah, so very down on its mood. Anyways, so the second derivative is less than 0, then that's our concave up. Yeah, Sage, I agree. I think we should all practice our addition and subtraction before the AP test. Okay, and finally, our points of inflection are just a change in concavity. So if we go from concave up to concave down, or vice versa. Yeah, thank you. I think Readings sent a very nice table. And yeah, so that's just combining our increasing, decreasing, as well as concavity in a table. All right. Okay, so now here's a sample problem on concavity. So we want to find all the intervals where the function is concave up or concave down, and then next find our points of inflection. So everyone, let's try to solve this problem. And again, just let me know whenever you solve so we don't dwell on a single problem for too long. So for the GE test, you have to input. So I think that's right, but I don't think it's the domain. I think it's the interval, unless if I'm misremembering something. Sorry, what was the GE test again? Was that global extrema? Okay, yeah. And yeah, so again, hopefully we're working on this problem, and yeah, so as Savage is saying, yeah, that's right, for candidates tests. I got confused there for second with G test, but I understand where that's coming from. So again, hopefully we are working on this problem, and yeah, so since we're working with concavity, we're going to be working with our second derivative, so hopefully that's the first step that we all took. And let me check, make sure my recording is still going. Okay, I think it's good. Excuse me. So have we managed to get a answer yet? Are we still working? Okay. So EVT includes absolute and relative. Well, so the EVT is trying to prove that absolute extrema exists. And yeah, the condition is when it's A to B. When A to B on a closed interval is continuous. So relative, I think that's more with the candidates test. Yeah. Because you would find the relative extrema with the critical points to test for your absolute, but EVT on its own is just about absolute. Yeah, Savage is explaining. Okay, so the solution I have is it's always concave up, it's never concave down, and there's no points of inflection. So hopefully I did it correctly, but if I made a mistake, please let me know. So our first derivative is this expression here, then we take the derivative again to get this expression. Then we have a very nice 12 times x minus 1 squared. So we just have a single potential point of inflection at x equals 1. And then we can test on intervals. Let me see. I don't think I should have plugged in 0. I think yeah, that should be 2. Sorry. Made a mistake when I was copying and pasting. So if we check on the first interval to the left of x equals 1, we see that our function is concave up. If we what's the word? If we look at the right side, right of x equals 1, we still have a positive second derivative, so it's still concave up. And yeah, well, my 2 cents, my calc teacher isn't really a fan of actually plugging in the values. I think she just expects us to do it in our head, but I don't know. Anyways, so hopefully this concavity makes sense. Okay, can you plug in your points? Well, if you plug in those points back, you would just get 0, because either 0 or yeah, just 0, because our points of inflection are where our second derivative yeah, you can plug it in back to the original function. I think that's what you meant, because if you just plug it back into your second derivative, you just get 0 again. Okay, so let's try to get through all the topics today. So next one, we have second derivative test. So with the second derivative test, it also is to determine if a critical point is a relative max or min, or neither. Neither. I'm not sure which one is correct. Anyways, so the first step is to find our critical points. The next step is to plug in our critical points into our second derivative, and if we have a concave up function, or if the function is concave up around that point, so positive second derivative, then it's a local minimum. If it's concave down, we have a local maximum. If not, it's inconclusive. We have to either use the first derivative test or some other means of finding our relative extrema. Okay, and then some words of caution. Second derivative test is not about points of inflection. So even though it's a second derivative, it's not about points of inflection. It's still about relative extrema. So please just keep that in mind. I know from experience, I've seen many people try to find points of inflection and cite the second derivative test, that's not true. And then if a, so let me see. Yeah, so this is the what's the word? Kind of the rule that I used back during that optimization problem. So if we have a single critical point, and that's a point is a relative extrema, that must be the absolute extrema on the interval. So I think some of us had some confusion about this concept. So again, if I have a function, and let's say on the current interval, I only have a single relative extrema. So this is a relative max. So basically what that statement is saying is that since we only have a single relative extrema in a single critical point, this must also be the absolute maximum. And so if we just look at it graphically, we can say, of course, that's the absolute max. However, we can generalize this idea to any case where we have just a single critical point, a single extreme of relative extrema. And if we have the single extrema, then that must also be the absolute extrema. Hopefully that makes sense for this topic, or rather this rule. But please let me know if that still doesn't make any sense. And I saw a request for the integration problem. I don't know, maybe if we have time I'll try it. But anyways, let's try to finish up all these topics at least. So here's a sample problem. Try to use the second derivative test to find all local extrema. And so you don't have to use the first derivative test as of now because we're running a bit short on time, but maybe later today you can double check your work with the first derivative test. Okay, yeah, thank you, Savage. So yeah, everyone just try to use the second derivative test here, and yeah, try to see if you can find any local extrema. Okay, we're almost there. I think we have 3 more topics left, and we'll try to finish before the 2-hour mark, so we should have enough time. So again, if you are stuck, remember we need to get our second derivative. So in the meanwhile, also take the first derivative, of course, so we can find critical points and then test concavity at those points. And then that's our second derivative test. Once you do that, you should be able to find our local extrema for this function. Okay. I think that should be correct. I recall square root of 2. I think even if it's not right, it should be close. So here, let's just take a look at the solution together. And yeah, so we have a local max at 0 and local min at both negative square root of 2 as well as square root of 2. And so note these aren't the actual maximum and minimum values. These are just where we have our extrema. So we can first take the first derivative and we can get our critical points here. Yeah, so don't forget the plus and minus part. And then we can take our second derivative and plug in our critical points here. So hopefully if I didn't make a mistake, this should be the right answer. So hopefully everyone is okay with this. And if so, let's move on to the graphs of functions and their derivatives. Okay, so this is basically how can we graph different functions based on what we know about their derivatives and vice versa. So these are just some general, oops, just some general clues and strategies on how we can graph. So if we have the first derivative, we know we have information about increasing and decreasing intervals as well as our critical points, and from there we can also potentially find our local extrema. So this will help us with graphing the original function. If we have the second derivative, this will give us information about whether f of x, so the original function, about concavity as well as potential points of inflection. So this second derivative graph can help with concavity. And yeah, so just some more tips. If we have the slope of f of x, so that's the derivative, that will help us with f prime of x. If we know the sign of our derivative, that helps us to find clues about f of x, particularly with increasing and decreasing. And then if we know the slope of our f double prime of x, actually I think that should be the other way around. If we know the slope of f prime of x, that gives us clues about our second derivative. Yeah, I believe that's the other way, unless if I'm thinking something wrong. Okay, so just some general strategies and ways of thinking. All right, so let's try to solve this problem. If we have this function f of x, x to the power of 3 minus 3x, try to sketch f of x, f prime of x, and f double prime of x. And this will just help us see some relationships between these functions and their derivatives. And right, so just again, let me know what your guys' progress is. I mean, yeah, you can use decimals to check your answer, but still, I think it's a good practice to make sure you can graph these. And I know you can just take the derivative and plug in points, but also try to, so for example, here I have f of x, so try to get a sense of what f prime of x will look like, what f double prime of x will look like. So if we had a MC question, for example, it might give you different graphs, and it may ask, okay, so given f of x, the graph of f of x, what is the graph of f prime of x? So try to use different clues about increasing, decreasing, critical points, points of inflection, concavity. Use all these tools together to try and... Yeah, I guess I should have, but technically that's different. That's integration, right? So that's a different unit. I guess I could have. But still, it's good just to get a sense of how these different graphs relate. Okay, so... No, I understand. It's all good. So, we're running a bit short on time. I'm just going to show my answer and you can check with what you have so far. So this is what I graphed with decimals. So here, these are just some important things to pay attention to. So where are our critical points? Where are we increasing and decreasing? So these will all help us when we graph our derivative function, because where it's increasing, we know it's positive. Where it's decreasing, we know it's negative. And critical points is where it's 0. And yeah, it's okay. As long as we just pay attention to some relationships, that's all I really want to take from this problem. And then yeah, so paying attention to where our local max and mins are, our points of inflection and concavity, this will help us with our second derivative. So yeah, so for further practice, just take different functions and then maybe start from the original function and then try to graph the derivative, or start from the derivative and try to graph the original. Just try to find these different patterns and relationships, so that will help you on your test. Okay, so this is similar to the previous topic. Just I forget what the exact difference between these two topics are, but just some more relationships between our derivatives. So if we have a local max and min, we want to remember that we have a critical point and a sign change in our derivative. If we have increasing and decreasing of the original function, that can help us with finding what the sign of the derivative is. And then similarly with concavity, we can find the sign of our second derivative. And then if we have points of inflection, that's, well, yeah, because with points of inflection, that means we have a sign change in f prime of x, so we know it must change sign there. Okay, so if the e x to the 4 minus pi x cubed, yeah, I think that, so are you asking if we had to graph that equation, or for the e to the x? Yeah, I think most of the time when they give a graphing question that they actually want you to draw it out, um, I think they just look for general things like, oh, if it's increasing is your derivative function. Yeah, as Savage said, most of the time it's just a rough sketch. So don't worry about it being exact. Okay, so here's a sample problem. We have a function f of x, and so we observe some things about this function. We know that it decreases until x equals 1, then increases until x equals 4, then decreases again. And on concavity, we know that it's concave up until x equals 2.5, then concave down. So try to draw rough sketches of f prime of x and f double prime of x. And I think I also drew f of x, but since we already know some things about f of x, it's all right if you don't graph that as well. So yeah, everyone, let's try to graph f prime of x and f double prime of x. So we have about 10 minutes left to the 2-hour mark, but I think it's fine. We should be able to cover the last topic within that time. And I'd be happy to stay a bit longer if we have any more questions. I might just end the recording at 2 hours. So again, if you need a hint, increasing, decreasing, critical points, extrema, these things will help us with f prime of x. Concave up, concave down, points of inflection, these will help us with second derivative. And actually, yeah, it's kind of hard to describe. So you don't have to give an answer, just let me know if you finish solving. And yeah, then we can take a look at the solution together. Okay, maybe 1 more minute. At least try to graph one of the graphs if you can, and we'll take a look at the solution together. Okay, hopefully you all were able to make some progress. So here, yeah, these are just some things to pay attention to. So for example, if it's decreasing to increasing, we know that's a local min. If we have a change in concavity, we know that's a point of inflection. So yeah, this is a, how would you describe it? Kind of a verbal description of the graph, but I also drew the graph myself. So hopefully these are accurate enough. So we can see here where it's concave up, where it's increasing and decreasing. And we can see here with our first derivative, it's an upside down parabola, or similar to an upside down parabola shape. because here we have, or did I do this wrong? Oh, no, right, because here up till 1 we have a decreasing slope, so it's below 0, then increasing, so above 0, then decreasing at 4, so we go below the x-axis, and you can see the change in concavity as well. That because a change in concavity, or rather not a change, but just concavity in general, that helps to tell us about whether the first derivative is increasing or decreasing. So here we can see it's increasing then decreasing. So yeah, and then with the second derivative graph, since we have concave up, then concave down, so I just drew it linearly because that's the simplest form. So hopefully these graphs are similar to what you have drawn. If I made a mistake here, please let me know, but hopefully these are all right. And yeah, so yeah, that's true. Just again, maybe go through the checklist, check if you're increasing, decreasing, things like that, if they match up. And as long as they do, they should be fine. Yeah, because on the actual AP test, they won't really care about how accurate it is. They'll just check things like, oh, is it concave up where it should be? Is it concave down where it should be? Okay, so this is our last topic. Let's try to end on a strong note. So behaviors of implicit relations. So an implicit relation is just some equation or function where it's not explicitly solved for y. So in other words, we need to use some implicit differentiation. And right, so for the first derivative, we can just use implicit differentiation to solve. And our critical points occur when we have dy dx is equal to 0, so that's a horizontal tangent, or when dy dx is undefined, that's a vertical tangent. And then for our second derivative, of course, this tells us about concavity. And when we take the derivative, we will often have to use the chain rule and plug in dy dx back into the second derivative. So let's try with the problem and see if we can use those ideas to solve. So given this implicit relation x squared plus y squared equals 25, find dy dx, all the critical points on the upper half of the circle. So if you didn't know already, this is our equation of a circle. And then finally find the second derivative in terms of x and y. And by the way, dy dx, I believe it's also in terms of x and y. So please try to find these. And yeah, so let me see, what are you guys talking about potential energy? I don't think we've done the integral of potential energy in mechanics. Okay, interesting conversation. Yeah, so again, everyone please be working on this problem. Let's end off strong. So you'll need to use your implicit differentiation, so hopefully you remember. And yeah, just remember what are the definition for critical points and implicit relations, and then when you find your second derivative, pay attention to chain rule, and then you can re-plug in dy dx if needed. Okay. So I'm just to finish before the 2-hour mark, I'm just going to show my answer here. So what I got for dy dx is negative x over y, and the critical point I got at 0, 5. And my second derivative, I got this expression here. So yeah, it's a bit hard to see in this format here. I'll just rewrite it on whiteboard. So we have x squared plus y squared equals 25, I believe. So if we take the derivative in terms of x on both sides, we get 2x plus 2y dy dx equals 0. So isolating for dy dx, we can subtract 2x on both sides and then divide by 2y. So dy dx, we get negative 2y over 2x. So I'll cancel the 2's, get negative y over x. And then our critical points are when this dy dx is either undefined or equal to 0. So if it's equal to 0, that means y has to be equal to 0. And in that case, if y is 0, we know x is equal to 5. So at one point would be 5 comma 0. And we only care about the top half, so any positive values of y. Actually, is that what I put here? Okay, I guess 5 comma 0 and negative 5 comma 0 should count, but they're like on the x-axis. So yeah, for 0 comma 5, that's when we have x is undefined. So when x is equal to 0, our y is equal to 0. So yeah, it's kind of my fault with the phrasing. Is it negative x over y? Oh, actually, oh yeah, you guys are right. Yeah, it should be x over y. That's my bad. Oh, is that why this part is wrong as well? So x over y. So with negative x over y, yeah, so if our derivative is equal to 0, that's our critical point. So where x is 0, yeah, and then y is equal to 5. Yeah, so then that's where we can get our critical point. Yeah, that's true. I think that would still affect the answer. And it would also affect our second derivative here. So to find that, we can take the derivative of our first derivative to get the second derivative. So we can do our quotient rule. So let's see. So it's low d high. Yes, low d high minus high d low, square the bottom. Okay, I hope that's right. And then we can, so let me first simplify. So it should be x dy dx minus y over, oops, minus y squared. Then we plug this back in. So we get negative x squared over y minus y over y squared. So it should be negative x squared minus y squared over y cubed. So let me see, did I do that correctly? Yeah, so I just factored out the negative. So I should be right. So hopefully this makes sense for everyone. So yeah, let me get this form ready one more time. So any final questions? If not, I'll just end the recording as well. So any more questions from you all? If not, I will... Yeah, I'm just going to end the recording now, and feel free to ask questions. I think I can stay a bit longer. So let me stop my recording.